All right. Well, we know the drill now. We're going to repeat pretty much what we started with, what we've done with momentum transport now with heat transport. So we will first start with the simple conceptual law, and we actually went over it already. In this case, it's not Newton's law anymore, but it's Fourier's law for heat conduction. And it's one of these simplest and most used laws that is basically connecting flux and gradient that is causing the transport in a linear way. So essentially we have that the flux in the simplest model that is one-dimensional. We have flux that is transported from the place of higher temperature to the place of lower temperature is basically proportional to the gradient of this temperature. So that essentially means that if I increase so I'm inversely proportional to the separation between the places. I'm directly proportional to the actual difference between the temperatures. And I'm when I'm thinking about the flux, I'm typically normalizing by the area. But if I were collecting the cumulative sum of it, it would grow with the area itself, right? So this coefficient K, which is thermal conductivity, in this particular case is assumed to be constant. Okay. However, if I change temperatures or absolute values of temperatures, so right now we don't have the direct dependence on the absolute value of the temperature in there, built in, but it's basically going to change somewhat with the change in temperature. Okay? So we have to think about this as sort of like fixed for a time, or this think about K as constant for the range of temperatures that we are looking at here. Okay? So that is pretty much equivalent to what was happening for Newton's law and viscosity of fluids as well. We were taking mu, or viscosity, as constant for the range of for the situation looked at. There it was a little simpler because yes, viscosity was something that was dependent on temperature, but we were always looking at isothermal systems. Okay? So in this case, well, it's not isothermal. Obviously, I have a gradient of temperature that is moving things around, right? But for the range of those temperatures, we're assuming K as constant. So just have that in mind. And we did actually look over some let's just, yeah, but I probably have to change, of course. Displays, okay. So just to review, so of course if I have a three-dimensional situation and not just my one-dimensional gradient anymore, then I have that the flux as a vector is directly proportional to the gradient vector, or vector as a gradient of temperature. So of course I could move in three different directions. In general, most of the time we're just going to look at K as a constant. However, in general, I could have some sort of anisotropic case where my K is actually dependent on the direction. That is going to typically be the case when I actually have something structural that imposes difference in different direction. So for instance, I might have a complex medium. Okay? So my effective thermal conductivity of this complex medium is dependent on the direction that I'm looking at, especially if there's some specific layering within the system that is imposing this anisotropicity. Other than that, I'm looking at if I have some sort of homogeneous matter, presumably there's no really difference in different directions. And my thermal conductivity units are basically derived from Fourier's law. So I have energy per time, okay? And then meter square is the area, and then I do the inverse meter over K for my gradient. So that is basically watt per meter Kelvin. Okay. One thing that we're gonna look at quite a bit is thermal, especially when we start at the end, we're gonna have sort of dimensional analysis. Then we're gonna look at these coefficients that are comparing different type of transport in the same manner. So basically, if I define thermal diffusivity, which is K divided by rho, and the thermal capacity per unit mass, then I'm going to get units of meter square per second, which allow me to compare it with kinematic viscosity, for instance. Okay? And that comparison typically gives me, well, which one of these types of transport is a dominant one that I should focus on. So one such number is Prandtl number, which is basically kinematic viscosity divided by thermal diffusivity, and also Peclet number, which also looks at the same thing, just multiplied by Reynolds number, which is a function of heat versus temperature gradient. So my heat, of course, could always move in with the fluid itself. Okay, so we are going to have convection as part of the transport mechanism for heat as well. But there could be also, if my momentum transport is much more dominant in terms of the speed of the development, then the heat transport from the heat gradient on its own, okay, then I technically don't need to look at the transport by heat gradient because I'm dominated by whatever just moves in with momentum transport. And that's what Peclet number for heat transfer is telling me. Peclet number will exist also for mass transfer and will have a similar form. Okay. So we have different tables in the textbook just to look at some of this behavior of the thermal conductivity versus temperature. And in essence, well, we were doing this guessing game last time around, but in essence, it's actually a little hard to pinpoint the precise dependence. So I will have thermal conductivity in general increase in temperature for some simple gases. Okay? But if I go to liquids, that might not be the case anymore. So I will have some of the liquids where I'm going to increase, but some of the liquids where I'm going to decrease, such as that pentane on top. So there is no precise rule, and therefore it's going to be also harder to get the theories that basically back up this data too. So this is some solids. Thermal conductivity of solids, of course, is much larger, well, especially for metallic solids, is much larger than most of the gases and liquids. So you can see sort of orders of difference in magnitude. Now, let's just quickly compare to what we know already. So we had momentum transfer, and our transport quantity was momentum, rho v, if I'm looking at the momentum density, or just mv. And then potential difference was that in velocities. And velocity in itself was a vector. Okay, and as a vector quantity, it's much more complex to look at the differences in velocities. So my driving force was actually tensor, because to look at how differences in vectors affect the flow, I have to actually look at all of the three different or three independent directions, or how it changes with respect to the three independent directions. So my flux quantity was stress, which was also tensor. And the stress was evaluated by looking at the forces across three different independent directions. Okay. Now my transport coefficient was still a simple one, or in most cases just a constant, and it's called viscosity. Now for heat, I'm going to have differences in temperature, and temperature is a scalar field. So my driving force is actually a gradient of temperature, and my resulting flux is a vector. It's not a tensor quantity. So it's going to be easier to look at in itself. The problem will come typically from the fact that whenever I have fluids, I'm going to have motion of fluids as well as heat transfer. So I'm going to have to couple two different types of transport. And decoupling them can get tricky. So let's look at just we will look at some very basic kinetic theory to look into the thermal conductivity as a coefficient. So let's start comparing. So we know for viscosity that viscosity of a gas at low density increases with increasing temperature, and for liquid it decreases. Okay? And well, for most liquids we're going to have a similar behavior. So for thermal conductivity, for gas at low density, it does increase with increasing temperature. We saw that in that first table that I showed. However, for liquid, it could be decrease or increase. Okay, and we had that in the table as well. So there is a molecular scale explanation. However, the theory is a little more difficult. So when we looked at viscosity of gases and look at just the fundamental theory to try to explain this phenomena, this was covered in our chapter 1.4. The basic idea was to look at a bunch of molecules that are moving around. Those molecules can have only elastic collisions because those are relatively easy to account for. And we're not looking at any intermolecular forces, which we know is actually quite an important thing to look at for realistic behavior, especially as my gases get more dense and molecules get closer. And in the limit, when I have phase transition to liquids, I have constantly neighbors that are very close to me and extremely complex force fields in between those molecules. And that's basically today handling those, even with the parallel computation in liquids, is extremely complex, okay, and difficult because there's way too many things to account for. However, kinetic theory still gave us some basic understanding of how things are happening. So what we were doing is like, okay, let's say that I have a bunch of molecules, and we imposed this difference in velocities, and we did our simple case of two parallel plates, right? And viscosity only, or the velocity only happening in one direction, and differences in basically across directions. So we had x direction velocity and differences in y direction. And then we basically looked at the kinetic theory of gases and what it gives us in terms of cumulative behavior of that gas. So we had expressions, those are statistical formulas, and one of them you derived for your homework. So basically that gives us independent look into what is happening and what is this cumulative behavior of molecules. And when we applied it, we actually saw that there is something like Newton's law that arises from this derivation. In effect, we had that tau yx is indeed proportional to the dvx dy, and that proportionality constant did not depend on velocity itself. So it was something that depends only on gas properties or molecular properties. Cool. So we can actually do similar thing for thermal conductivity. Okay? So this is covered in chapter 9.1 in your textbook, and the basic idea is similar. Impose a gradient in temperature across gas phase, derive expression for flux of kinetic energy this time, okay? And use the results from kinetic theory to relate that temperature difference to other properties. So we can actually look at the flux of kinetic energy and this gradient in temperature and see whether they're proportional as per Fourier's law. Essentially compare to Fourier's law and see whether they compare well and what the comparison is. So let's do that. Okay? This is pretty much the same slide that I had in our initial lecture. So I have gas, and I have gas in random motion at low density and elastic collisions. And this time, the only difference I made is what is it that I have gradient of. Good old cut, copy, paste with a couple of changes, right? But that shows you the similarities essentially. So now I have temperature differences, and I have a higher temperature at lower values of y and a lower temperature at higher values of y. So we're going to put an imaginary plane again, okay, at value y. And then I have temperature at y minus a and y plus a, where a, so whenever I have molecules bouncing around, okay, I have mean free path, which is sort of an average statistical distance between two collisions. However, that could be oriented in any way. So on average, the actual distance in one of the coordinate dimensions between the two is 2/3 of that. Okay. So my A is then that coordinate plane difference between two, or average coordinate plane difference between two collisions. And that's given as 2/3 lambda, where lambda depends on the diameter of molecules and their number density. Okay, so how many molecules do I have per unit volume? Now, average speed, velocity field is randomly oriented, so presumably whichever direction I look, I will have the same distribution of the velocity directions, but their speed is actually related to the temperature. So this is a great result that basically gives me some average behavior, which is temperature, which I measure macroscopically, and the speed of molecular movement, and that's where the Boltzmann constant comes in, as well as the mass of the molecule. And then we also had the frequency of molecular bombardment of one side, bottom or the top, surface exposed to gas, and that is related to the velocity, to the speed. Okay. And of course, the number of molecules. Cool. So I know these results already. So let's look at what it is that I'm transporting. So molecules are moving around, and now I'm looking at the heat, which is energy transport. And the only energy that we are actually looking into is kinetic energy, and that's also the only energy that these two molecules exchange as they collide. So basically I have energy is 1/2 mass times average of U squared. And average of U squared in itself is not that expression averaged. Okay, I have an integral of U squared that I have to do over the distribution of velocities, but you can look into this problem if you want to, but basically energy is directly related to the temperature via Boltzmann constant. Cool. So I know what I'm exchanging. So now we're going to go the same way we went before. Okay? At my plane y, okay, I'm going to look at the molecules that are crossing upwards, and they carry certain energy with them. What is that energy? Where is that energy from? Well, that energy is related to their last collision. That's where there was an exchange. And that energy is also related to the temperature field at the point of that last collision. Okay? And then I'm going to count how many of them are moving upwards across the plane, and how many of them are moving downwards, and what their energy is, and just subtract the two. And that's basically what's moving across a plane. Cool. Whoops. So I impose this temperature gradient, and of course I'm going to look at the standard approximation that I have from Taylor's formula. Again, if you carry anything from your calculus 1, that should be Taylor's formula. You can forget everything else. That's one of the key results you should not forget. Nobody tells you that when you're actually studying calculus. Like, look at this formula. It's going to show up throughout your engineering education. So T at y plus minus a is the same as Ty plus minus a dt dy, and I'm cut off all of the second order and terms and higher. Cool. So let's get going. So my heat flux across this y plane is the energy or kinetic energy of all molecules crossing in plus y direction minus that of molecules crossing in minus y. So how many of them Z, that's my frequency of molecular bombardment, and I need to evaluate energy at the last collision, which for those moving in plus y direction was at y minus a, at that plane. And I have to subtract, again, my average number of molecules is still Z, but they had those molecules that are crossing in minus y direction are carrying different kinetic energy because they come from a place of different temperature. And my kinetic energy is directly related to the temperature. So I put that in. And basically, this is where I put Taylor formulas in for the difference between the temperature at y minus a and y plus a. And that is minus spacing between them, minus 2a dt dy, according to Taylor's formula. And the rest is just now a bunch of algebra. So when I put that together, I'm going to see that my flux in y direction is something that I can couple or put together as just depending, it's a property depending only on the gas itself. So it's number density, this is related to the mass and diameter of the molecules, and dt dy. So this is essentially what my thermal conductivity is. I can clean it up in one way or the other, but I have dependence on the diameter of the molecules, mass of the molecules, current temperature, and the rest is a Boltzmann constant NP. Okay. So I do depend on the temperature itself, so I do get the temperature dependence, okay, for gases at low density. And as my temperature increases, so does my thermal conductivity. Let's quickly just go back to confirm that. Is this gases? Yes. So as my temperature increases, so does my thermal conductivity. This one, yes, increases, increases, increases. Okay? So for simple gases, for liquids not so much, but for gases this works. Okay. What was the dependence of viscosity on temperature based on kinetic theory? So no, square root of T. So when I have these little tennis balls on the molecular scale, it seems that all of the transport properties have the same origin and kind of they look the same as well. Not so much as you start adding the molecular forces and so forth, but there is certain basic for the gases at low density. There's actually all of the properties kind of come down to the same thing. And we also had, as a result of that, if you remember that Prandtl number was pretty similar to 1. It was 0.7 or so for the two different types of transport. Okay? So for gases, everything ends up being the same. It's for the liquids and solids where things are vastly different because I have emergence of structures and the molecular forces surrounding each molecule that are creating a much more complex situation. Right. So if you compare to what we had before, this was the relationship we got for viscosity in our chapter 1.4. All right. Now, in this case, of course, we could also correct for this intermolecular repulsive and attractive forces, and that is done here. I'm just mentioning it and mentioning the final formula, similar as in our chapter. So we have basically the Lennard-Jones potential, okay, phi, and then the force between the two molecules at distance r is the derivative with respect to the distance of that potential, and this is the potential formula. There's a couple of different variations of this formula, but overall this one works really well. if you were, though, to implement this, so this is something that is, when you think about there's a lot of simulators nowadays that are simulating molecular collisions in transport. Okay? And this would be the standard thing that you would put in there. So you're basically, you drop in however many molecules you want in your box. Okay? And for every 2 molecules, it's relatively easy to compute the distance between them, r. Right? And then this is your potential and force in between them. Now, of course, for every molecule, you have to sum up all of the forces that are happening on that molecule in that box. Right? So sum up of all of the terms like this, however simple they are to compute. If you're tracking 100,000 molecules, that's a problem. And we know that 100,000 is nothing. How many molecules do I have in a mole? Good luck computing. So then all of these, you need heavy parallel computing to actually account for all of these, even though it looks actually relatively simple. There's nothing really to it. It's like, here are the forces, sum them all up, and then you just have Newton's law. Right? And mass times acceleration is the sum of all of the forces. Move that molecule based on that rule. That's all there is to it, really, to molecular simulation. Except that you have to track so many particles that it becomes intractable. And of course, as you add different types, so this is for the same type of particles, as you add different types of particles, then your intermolecular forces become complicated. Right? And that's what we'd like to do. So in petroleum engineering, we'd like to see, I have surfaces that have attract different mineral properties, and I might have different attraction forces to different types of fluids and so forth. Can I see the emergence of a contact angle? By the time you put enough molecules in the box and have boundary conditions, as we learned, are always an issue. So setting up boundary conditions that are relatively realistic and are not too small. Our boundary conditions, or knowledge of them, comes from sort of core scale type of experiments. So what do you put as boundary conditions for a molecular type of simulation that goes over 20 nanometers? So those are the typical issues that we have in the simulation. And then where do you cut things off? So if I'm tracking 1 mole, 10 to the 23 of molecules, I'm not going to compute this force field for all of the 10 to the 23 molecules at the same time. I should kind of localize it and chop this off. So this is why it's actually important to look at this intermolecular distance and say, okay, if my distance is smaller than a certain number, at zero it out. So don't compute for those molecules that are too far away. And too far away is how many normalized distances? Somewhere between 2 and 3, right? So that's why it's important to actually look at this critically when you're setting up simulations, even though it actually analytically it looks really simple. But in this case, analytically it's simple, but tracking down over everything that you need to track down is complicated. There's a lot of research in terms of molecular type of simulation was out of, or was not really done in petroleum engineering almost at all. It's mostly chemistry, up until shales. And that is mud rocks, where we're now trying to evaluate, okay, well, what is happening really on nanometer scale, where all of our continuum type of modeling is breaking down if I have a channel that is 10 to 20 nanometer across. And basically my formulas like Navier-Stokes and so forth are not necessarily representative anymore. They have the boundary conditions we're not used to. The walls are way too close. So if I'm colliding with the walls more often than I'm colliding with the molecules of the same type, then my continuum type of thinking of a phase is breaking down. And that's where there's actually quite a bit of now molecular type of simulations on that scale to actually see what is happening and what is the proper way to account for things. So that is just commentary on how is this used in the current research, but we can actually adjust my thermal conductivity, and I will look at the same collision operator that we've looked at for viscosity. So that is given in tables at the back of the book, and you can compute a better estimate for thermal conductivity if you wanted sort of an independent confirmation. Okay, so if you compare that to what we had for viscosity, you can see somewhat similar performance. Okay. Overall, however, so this explains me, at least for gases at low density, I have now understanding or independent confirmation of this behavior that thermal conductivity increases with increased temperature. Okay? For liquids, we're not going to go there. Okay? It's just too much hassle. However, not even experimental data shows clear trend, so I'm not sure what to go and confirm then. So all theories still need calibration with experimental data, so most of the time one actually goes to experimental data for thermal conductivity. All right. Now, this was all discussion for homogeneous matter. Often we will actually have composite, either solids or liquids, and therefore we need to actually go and look at some sort of effective property, or what is effective property depending on the fraction of individual components. As usual, we would always like to have just dependence on simple fractions. We actually know better, so it's not just simple fractions, it's also their spatial arrangement and how things connect on the small scale that actually affect the properties as well. That was the case in momentum transport. That is the case in thermal transport as well. So for instance, when I'm looking at this actual medium that presumably is just having spherical inclusions, okay? Spherical inclusions as drawn here are disconnected, okay, from each other and therefore not in direct contact. That is obviously a different situation from having, let's say, just like stripes across that are connected, because then those stripes present sort of like highways. Let's assume that these inclusions are of a higher thermal conductivity. Then suddenly those stripes are sort of highways for transport across, just like fractures are. Okay? So then that transport potentially happens on a whole different scale, or it could be orders of magnitude different. Okay? So then I end up dominated by those stripes of higher thermal conductivity. And if that thermal conductivity is, let's say, 10 times larger than the rest of the matrix, then I don't even have a notion that there's this rest exists in my medium, right? So obviously a simple volume average is not always applicable, okay? Because simple mixture is just going to take, a fraction of this matter times K1 plus a fraction, or I'm calling them K0 and K1. So a fraction of 1 times K0 plus a fraction of K of the other times K1, and that's it, right? And those simple mixtures, they're always the simplest to try. We always work with those the most. However, our porous structures of interest are typically either at least one of these phases is continuous and often bicontinuous. So both of them are flowing sort of or going across in parallel. For instance, if I have a simple sphere pack or a sandstone, especially if I have a sandstone, then both pores and solids are continuous across. Right? They interact, but they're also continuous across, and that affects my transport properties, thermal properties included. That said, there's a whole bunch of simple formulas for cases where I actually just have spherical inclusions, and there's a lot of man-made materials that are in this category. Okay. So I simply go by volume fraction of these spherical inclusions, which if it's small, then they're separated. They're not necessarily clumping together. And then I get an effective thermal conductivity of the composite. Okay? And what I mean always by an effective property is that I simply do a simple transport across this medium and compare it to Fourier's law. It was Newton's law before, it's Fourier's law here. So I'm looking at just this average thermal conductivity, and that's precisely what I would, if I was measuring this medium without knowing what it is, that's what I would be measuring in the lab, effective. Okay? That's always what I'm measuring in the lab, regardless of whether the medium is homogeneous or heterogeneous in structure. Because when we are measuring, we are essentially comparing to whatever law we have in mind. Okay, so in thermal conductivity, we are comparing it to Fourier's law. So again, in actuality, this thermal conductivity is some complex function of both the individual ones, these shapes of these inclusions and their spatial distribution and how they connect. However, effectively, we simply measure what we see on the outside, assuming I averaged a large enough sample to be representative of the medium. So there is actually a Maxwell's derivation for the effective thermal conductivity of composite, which is when compared to this K0. So K0 again is this matrix surrounding the inclusions. Then it's a function of both K0, K1, and the fraction T.
So are there other equations for effective conductivity when you have more than two solids?
Yeah, you could actually go kind of recursively and apply this technically. You can assume, clump two of them together, right? And call that K1, and then develop what that is inside of this. That would be an option. So you could play with that yourself. Basically, you pair two together and consider them as one, and then you have two, and then you write this formula, and then the one that you paired together, you unwrap. That would be one. That would be recursive. If you can spatially clump them together so that they obey this same law.
Okay.
What's often done, though, and that's going to be your homework exercise, is parallel and series model. And that can be done for any type of transport property, really. It's basically it's a sample transistor-resistor network model. So just put them either in series or in parallel. And in both cases, you could have a number of things connected in series or parallel, and you basically just do average across from that.
Okay.
And that can be done again for any property. So you're going to have that exercise for your homework. So when I think in series versus parallel, that's where you could actually have this case of, let's say that you have layers. Right? So if you're transporting parallel to the layers, okay, they're all in parallel. They're acting in parallel. Whereas if you're actually going the other in the cross direction, they're in series because basically, essentially, the one that is the throat or the bottleneck will end up being the dominant one when they all have to go through each other to go across. Right? So those are the two end members in any type of modeling. Those are your two end members in this how could I connect on the small scale type of flow. And those are the simplest models that you look at. So again, they apply for any type of transport, but it's going to be a homework exercise too. All right. So what would you get if your K1 was way smaller than K0? So if you divide this by K1 and this by K1 and take a limit, this becomes 1. So then all you have is 1 plus 3 phi over 1 minus phi. So you can, when you have a nice formula like that, you can play with limits and behavior, which is always the benefit of having a formula. And if you have something that is ultimately too complex, then you just have to do a simulation to actually figure out, or an experiment to actually figure out what's going on. So that's all great. This was all actually kind of solids. I didn't assume any fluid movement so far in discussing transport properties. In that considering bouncing balls, I did apply the thermal gradient, but I wasn't moving the phase convectively. Right? So now it's time to consider actually what is carried into a fluid, into a element, volume element, simply by the bulk motion. Right? Well, so my kinetic energy per unit volume is, or 1/2 rho v squared, right? So if I have a static box of fluid like this one, and fluid is actually moving here, and in addition I also have a thermal gradient, then if I'm looking at the equations that are just in the static coordinate system, so then this control volume is not moving with the fluid, therefore it's constantly sampling different part of fluid as it's moving in. And whatever is moving in is also bringing in its kinetic energy. So I have that in parallel, whatever motion would be there simply by the imposed thermal gradient without the bulk motion. Okay. So we are basically mathematically separating the two, even though everything is happening at the same time. And if I was doing the experiment, it would be extremely hard to decouple the two. Okay. I can do that if I have equations a little better. So this is my kinetic energy, so this is what can actually get moved in. And I also have certain internal energy per unit volume, and this unit volume will have a little, per unit volume will have a little hat above. Okay? So basically rate of energy per unit area that is carried into an element. So let's say that this is my x side. Okay? So what's carried into the element is orthogonal to that side. And in this particular case, for x direction, is then carried into only with Vx. Okay. So this is what's carried around, and this is the component of the velocity normal to the surface that I'm looking at. And that is, in this case, Vx. Otherwise, it's Vn, where Vn is a projection onto the normal of whatever surface I'm looking at. So the only things that are carried into, and I keep repeating this from the beginning of the course, whatever you carry into is always just the component that is normal to the surface you're going across. Otherwise, all of the tangential parts are basically sliding around that volume and not going in. So they cannot change the energy that is inside the volume. Okay. So my convective energy flux vector, that is the equivalent of my rho VV from the equation of motion, is basically the energy that I carry times V. Okay. So in rho VV, what I was carrying in was rho V. So rho V, V, right? And here I just have energy V. Yes? So it is the same structure. Again, if I had some general surface, then all I would account for would be V dot n and times that surface. That's what's coming in, times the area of that surface, which is the total that is coming in through that surface. And I would have to integrate as well.
What is that?
Normal. So it's normal to a surface element. Some general normal in whatever direction. So here we're just looking at the coordinate surface, right? And therefore, that's why I'm getting Vx. Because V dot E dx is E Vx. And the same would be for y and z directions. Okay? Yes.
It's a silly question, but how are you bringing internal energy into a system?
So you can think about this square here, right?
Yeah.
Okay. My coordinate system and my equations are tied to the coordinate system that is static. Okay? But my volume is literally walking by. So as I'm walking in, I'm bringing my energy. Whatever breakfast I had this morning, I'm bringing it in.
Okay.
Okay? But my equations are just sitting here and accounting for everything. So I gotta account for simply the energy that is brought in.
And then also the kinetic energy.
So this is the kinetic energy walking into my static volume.
Okay.
So my equations are tied to the coordinate system and they're sitting still, right? They're not moving with the volume. Okay? I'm evaluating them just at fixed points, x, y, z, whatever it is that I set. Wherever it is, I can decide for my coordinate system to be whatever, and for my starting point of the coordinate system to be whatever. But once I do, it's fixed, right? Whereas my fluid is moving around. Okay? So that fluid, there's some of it that will simply be, if fluid is not moving around, okay, then what's moving things in terms of heat transport is just that difference in temperature. So that would be the only thing. So I can just look at that energy flux. However, if at the same time, but I'm not moving the fluid, right? Fluid is sitting still in this box, and the only thing that is passing through is like I have higher temperature there and lower temperature there, so there will be these molecular collisions that will just move like a wave through me. But I'm sitting still. The same particles are sitting in this box. Okay? Now I have that, but if there is also a gradient in pressure, that's moving different types of particles through this. So to account for all of the energy that is moving through this box, I gotta account for all of those different particles that are moving in. Literally, you come running by, right? I'm sitting still here, whatever, moving, because of some molecular the collisions that are coming as a wave through me, right? Even if I'm not, let's say that I'm tied in somehow here to this box. But if you are running through, I gotta account for that. And you're running through not because of the thermal gradient, but because of the pressure gradient, right? So it's a different type of forcing. And mathematical formulas, they tend to decouple all of the individual components. Because then I can just throw them away if they're not present in my current situation. So that's, and also I can look at the individual contributions. That's the value of having models. Because models have different sort of compartments for different type of contributions that I can turn on and off artificially to see what's happening. Whereas in reality, I can't always turn things off. I can't turn off gravity. I can in my simulation and just zero out. G equals to 0. It's that simple, right? But I can't do that in my experiment. And that's the value of having those two different things. Okay. So essentially, I do have to account for both those molecules that haven't necessarily moved, or simply they're getting jiggled by the temperature difference, and those that are running through because of their have some different type of forcing them through. Okay? And that's the convection part. Just a moment. Let me stop recording.